Hello everyone, welcome back to the SWAM NPTEL course on engineering aspects of biofuels and biomass conversion technologies. I am Professor Ijaz Ahmed, currently Assistant Professor in the Department of Chemical Engineering at IIT ISM Dhanbad. In Module 4, we are discussing about the gasifier stove, household gasifier as well as the commercial gasifier. So previously, if you remember, we discussed about the commercial gasifier stove. In the lecture 3, we will discuss about the household gasifier stove. In the previous class, we were discussing about the commercial gasifier stove operation. So the operation is very simple. It's not rocket science. You know, there is a fuel chamber. So you will open the lid, feed the fuel into that. You will close the lid and then you will seal it with the water. So you will fill the water seal with the water to prevent the gas leakage, and followed by that you will ignite through the ash pit door to burn the fuel, and then gasification starts. Okay. So this is, and then this is because there is a whole lot of biomass storage. You are able to run it for a long time, or you can run it for at commercial scale. So after 5 minutes, once you torch the light, you'll remove the torch and close the ash pit door, because if ash pit door is open, it will lead to the uncontrolled flow of the primary air, and then you may not get the desired producer gas or syngas quality that you want. So once you remove the ignition torch, the ignition will start building gradually, and within 20 minutes, you will see the producer gas or syngas will start coming out at the gas burner. Okay. Now, then again, because you want to use that producer gas, you ignite it at the burner, and then you start cooking whatever you want. In the burner, you know that there is secondary air. You don't have to supply the secondary air. The burner itself, the pipe is designed in such a way with the perforated holes that it can suck the air while gas is moving upward from the gasifier to the burner. Once lit, the gas flows becomes steady and continuous, and the stove can run for several hours on a single fuel load, because you see a lot of fuel can be stored in the fuel chamber. Okay, and then more fuel can also be added through the top of fuel chamber to extend the operating time. Periodically, you can after 20 minutes or 1 hour or some time, whatever, depending on how much fuel you have used and what is the ash content, you can use the ash scraper to break the accumulated ash inside the reaction chamber, and then to ensure uninterrupted downward flow of fresh fuel into the combustion zone. Now let's discuss about the household biomass gasifier stove and its working principle. So working principle is similar to that what we learned for the commercial gasifier. So you have the biomass here. It's you can see this looks like a IDD design. So you have the biomass here. The air is going from the bottom, and then you have combustion zone which is moving downward, and then you have char which is left behind by the combustion zone. And in this, not the combustion, it's, you remember that it's partial combustion, so it's a oxidation. This consists of oxidation, pyrolysis, as well as the reduction part as well. Okay, and the gas moves upward, and then you get the gas generated through the gasification. So we see that it is operated by same that we have learned earlier, by partial burning of rice husk or bagasse or any kind of biomass with a limited air supply to produce the combustible gases. The combustible gases that I told you earlier is like carbon monoxide, hydrogen, CH4. These are the main flammable gases, but you will also have CO2, which are, and the water vapor, which are non-combustible gases. Okay, so that you get as a byproduct, and by and large, there is not much control on that. The char formation occurs during the partial combustion, and this char again reacts with further with air and gases to produce the producer gas or the syngas. Okay. Now, if you look at what happens, that it's not just combustion, as I told you, the lot of process happens, and that includes, I would discuss drying, pyrolysis, oxidation, and reduction. But herein, what you do, the gas quality also depends on the air. The reason is, as I told you in the beginning, that only 30 to 40% of the stoichiometric air is supplied for the gasification. If you supply near to 100%, it will go under combustion rather than going under the gasification. So in this case, airflow is regulated by a small fan to maintain the proper gasification conditions. Now the fuel is ignited from the top of the chamber because this is initially fully filled with the fuel, and then gradually this will start moving down. Okay. So the combustion zone moves downward through the fuel at a rate of 1 to 2 centimeter per minute depending on how much air you have supplied. More the air, faster is the downward combustion. Less air slows the process, but then there is a limit how much air you can give. You always remember the limit should be between 30 to 40%, not more than that. And as the combustion zone descends, the char remains, which here will also react with the air to produce more syngas or the producer gas. Now after that, that gas will we have to burn, because in houses we don't use the commercial one, we use the small unit. So we have again a gas burner, but this is fitted on the top of the household gasifier. I'll show you on the image. So the gas, combustible gases will go through it. It will have secondary air coming, and then here when you will ignite this, you will get the flame. So if we look at the combustible gas flow and the burner operation, the combustible gases flow from downward to the upward to the burner holes, and secondary air mixes with the gas through the peripheral holes for proper ignition, and when you burn it, a luminous blue flame is ignited. Okay. Now in this also you need to control the air. Okay. Now for that, because that will actually define your flame of that. So a rotary switch controls the fan speed and air supply. If you have, or if you don't have, you will have, you can't do anything. If you do clockwise rotation, it increases fan speed and more air, more fuel burns. While if you do clockwise rotation, it increases the fan speed, the more air, then more fuel will burn. If you do counterclockwise rotation, it increases the fan speed, and when fan speed increases, you will have more air. When you will have more air, more fuel will burn. While if you do counterclockwise rotation, it will decrease the fan speed, and when fan speed is decreased, it will get less air, and then combustion will be slower. Okay. Now the flame color usually depends on the air supply, also on the composition of the gas, but it also depends on the air supply. So more air, that means blue flame. The less air, that means you will have a dull flame. Okay. This is something you have to remember. This is a typical design. So as I was saying, like unlike commercial gasifier, which has two zone, one is gasification zone, one is combustion zone. This has one. So this is only your fuel, combustion, everything is here. Okay. And this is your burner and the combustion zone, you can say. So this is gasification, and this is, I would say, gas combustion zone. Okay. Now this is, if you look at herein, we have a gasifier reactor. Okay. We fill it with the biomass. Then we have a fan which supplies the air here, and we ignite it initially. The biomass will get, so we ignite usually from here, the biomass will get ignited. Okay. And then it will develop to a full gasification, and usually gradually the gasification zone will start going down, leaving behind the char. Okay. And then the char, when falls down, can go to the bottom. Okay. So here in this case, let's say if the gasification is happening in the hole, so char will go down, and then you have, again you can remove the char from this section. But because during this gasification, the whole, this outer casing, because there is a lot of heat generated, it becomes very hard. So if you can't touch it, if you touch it, fingers might get burned. Therefore we put a safety shield here. Now let's say this biomass is charged into this. The gas is produced, gas is going up, it will suck the air from these holes, and then you ignite here, it will start giving you flame, you put the pot in it and you start cooking. Okay, so what happens? Firstly, the biomass is loaded into this hopper, which is also the gasifier, and then you supply the limited air 20 to 40% of a stoichiometric to produce the producer gas, that includes CO, H2 and CH4. Now the gas will burn down here with the high temperature and clean burning, which is suitable for the cooking. Okay. Some designs also uses natural draft. Okay, while some uses forced draft. So as I said, in the rural areas where you run out of electricity, you can't use a forced draft. You can't have a fan, so you can use a natural draft, or you can, if you are in urban city where the electricity is available, or in the rural area also where the electricity is available, you can use the fan here, which makes it a forced draft. So what happens once this is filled with the biomass, the primary air will enter through the bottom grate to add on to the gasification, and secondary air will come here to add into the clean gas combustion. Now, if I say the forced draft has either DC or AC powered fans, and typically the fan speed controller or regulator like we have in the houses. How do we control the speed of the fan? Similarly, we can control the speed of this fan, and accordingly we can control the gasification rate. If we talk about the construction material, it is built using mild steel, stainless steel or locally available materials, but it necessarily has to be lined with refractory cement. Okay, otherwise there will be huge heat losses. Particularly we use castable 13 for high temperature resistance. In some cases you will see it will become red hot if there is no refractory used. Chimneys or sills may also be added to prevent the direct smoke or the burns, which is a good idea, but it again depends that who is the user and what is the demography of the user. If the user is in rural area where many of the things are not available, putting a chimney, or for such a small scale unit, putting a chimney may be a challenging task. However, it's an undeniable fact that the household biomass gas stoves are very good low cost cooking solution for rural and semi-urban households. It reduces the reliance on LPG, kerosene and firewood, and by doing this we reduce our dependence on the import of the oil and gas, as well as, I mean, by using the firewood in much cleaner way, we also reduce the environmental load or the environmental pollution, because it produces less smoke and lower emissions compared to the traditional chulhas. It allows the efficient fuel usage that can cook with the less biomass, because when there is more efficiency you are getting, you can cook with the less biomass. The best part is that it can be operated using agricultural residues like rice husk, sawdust, briquettes, coconut shells, corn cobs, wood pellets, etc. Okay. Now, having said so many advantages, it has also some limitations. For example, it required dry and uniform fuel for best performance. Okay. Now, drying itself is a challenging task. If you go for natural drying, it will take days, while if you try to dry the feedstock using a commercial dryer, then it will require a lot of energy. Ash buildup needs regular removal, otherwise the whole gasifier chamber will get filled gradually over the time. The startup time is 15 to 20 minutes, which is longer than LPG, which burns in seconds. Okay. The safety consideration needed for high temperature components, like we have put a shield here, some people don't put the shield. And the forced draft stoves requires a reliable power source, particularly the image that you see here. This definitely requires a power source. Otherwise, we will have to remove the fan and we will have to use a natural draft household biomass gas stove. Now, If we look at the design, so this is the household biomass gas stove reactor. This is how it looks from inside. You can see this is an iron sheet molded into a cylindrical reaction chamber. Now in this, we fill the biomass. So you can say the reactor is the main chamber where biomass is loaded and gasified using limited supply. You can see this has a cylindrical shape which is much preferred. The diameter of this is usually between 0.1 to 0.3 meters. It also depends on the stove power output that you require, whereas the height varies between 0.4 to 1 meter based on the desired operating duration. More is the height, more biomass you can fill, and then for longer run, you can use it for long period of time. Similarly, we have fuel grade system. So it's a stainless steel grate. You know the grate like we discussed in the commercial gasifiers to remove the ash, allow the ash to fall down. Okay. So it is definitely fixed in the bottom of the reactor. Okay. To support the biomass. So it does two things. One, it supports the biomass, and also it allows later on to clean it. The grate is designed to be inclined, allowing the easy discharge of char after use, as I said earlier. It is held placed using a spring or locking mechanism for proper positioning during the operation. Usually circular metal rings on the outside of the reactor support and an aluminum safety screen. Okay. The screen prevents accidental contact like you see this. The accidental contact with the hard surfaces protecting the users during the operation. However, as I said, it is not necessary. It can be like without a screen shield as well. Now the second part, once this is filled, the second part is the char chamber, where your char after falling down from here gets collected and then we remove it using the ash scrappers. So it acts as a storage compartment for char produced during the gasification, also for the ash. Therefore, it is located directly beneath the gasification reactor chamber. Okay, so that whatever falls from there, it gets. So this is the gasification reactor, and whatever will fall from here, it will get collected here easily. Now, because it gets fitted, we have to clean it on a regular basis. So it is also fitted with a door for easy removal of accumulated char. And however, this must be closed during the operation. Otherwise, there will be uncontrolled flow of the primary air, and that will eventually affect the system efficiency. Particularly, this is a airtight construction. It is the whole chamber is sealed by tightly on all sides to prevent the fan driven air from escaping, also to maintain proper draft for efficient gasification. And the structural support is equipped with the legs, each fitted with a rubber cap. These legs support the entire stove structure and enhance the stability. Then coming to the fan assembly. So this is the fan assembly we are talking about. In actual how it looks like. This is also actual image, but this is zoomed out. So if you will see here, we have a fan. Okay. So it primary job is to supply the air for gasification of biomass fuel. It is usually mounted on the fuel chamber. You can see here, either through door or through the body. It allows direct airflow into the reactor fuel column, and then for that it uses a 3-inch axial fan commonly found in computers, etc. The power source is approximately 16 watts operated at 220 volt. It is from one kind of fan that I'm talking about. You can definitely take a different kind and different capacity fan depending on the kind of usage you have and the amount of gasification rate that you want. Now the manual rotary switch controls the fan speed and thereby regulates the gas flow to the burner. Then the most important part is this gas burner. Now herein we have, these are the secondary air holes, you can see. This is here you will torch and you will ignite to produce the flame. So if I talk about the gas burner, it converts the producer gas coming from this reactor to the clean bluish flame suitable for cooking, and it contains a series of 3 by 8 inch holes through which the combustible gas exit for ignition. So like this. The principal peripheral holes supply secondary air needed for complete combustion, and a port support is positioned on the top to hold cooking vessel securely during the use. This burner is removable, allowing for easy fuel loading into the reactor. So you can open it like this, and then you can easily reload the reactor and reinstall the later on to start the process. So as I said that this is what typically the whole biomass household biomass gasifier stove looks like. This is the reaction chamber in which the biomass is fed. This is the safety seal which help us to prevent from the what you can say the getting in direct contact with the hot chamber. So firstly the biomass is fed, then the important part is the fan which supplies 20 to 40% stoichiometric air to generate the producer gas. This we already discussed previously. Okay. Now this gas burns with a clean high temperature flame suitable for cooking. Okay. And as I said, this can be natural draft or this can be forced draft. Now, some of the classical household gasifier used since centuries is one here. You can say this is a DA IRRI rice husk gasifier stove, which is of downdraft type. So rice husk and air is fed from the top, and here the gasification happens, and that gasified gas goes through the cooling tank, so that if there is any non-condensable gas, it will get condensed here, while the other gases will get cleaned and go to the blower. Okay. Similarly, the another most common gasifier that has been used earlier days is the CPU single based burner batch type rice husk gasifier stove. This is also a downdraft gasifier. So if you will see here, the gas is fed from the top, and then you have combustion zone, and then you take the gases out to the cleaning or the direct usage section. Now the another kind of household biomass gasifier stove is like this is CPU prototype. You can see here this is a inverted downdraft gasifier. So you remember inverted downdraft, that means my biomass is here, this is my pyrolysis zone, let's say, and this is my charge zone. Okay, these two images actually shows the inverted downdraft gasifier. The air goes from here. If it could have been updraft gasifier, what will happen here? Like you have mass biomass, here you have charge. In updraft the air goes like this, the gas goes like this is very common. But what happens in case of IDD? In case of IDD, here you have char. Gas is going up, okay, and product coming out from here. While in this case, if you put the biomass in the bottom, sorry, you put the biomass here in the bottom. While in case of updraft gasifier, you put the biomass on the top. And then you have reduction and gasification zone here. You have some pyrolysis zone. So the air goes from bottom, and what you get, the gases are at the top. So this is a IDD rice husk gas stove, or it is also known as top lit gasifier stove. This is another CPU cross flow type rice husk gasifier stove. You can see now herein what you can see is that this is the gasification unit. I have my biomass herein. I am giving the air supply. Here the gas is coming, and then this is a burner where you burn it, and then you cook whatever. This is the, I think it appears to me like a fry pan or maybe a gas cooker that can be used to cook. Okay, so if you look at the household and commercial gasifiers, primarily you say the principle of the gasification remains same, the principle of heating remains same, everything is same. What is changing? That if I talk of household, it is a small batch process, a small batch, and then you can choose any. While for commercial, what you need is a continuous process and relatively large scale, and then others. But one thing should not be confused, that it's not necessary that a household gasifier cannot be a continuous gasifier. It can be a continuous gasifier. Okay. So there should be no doubt in it. Similarly, there are other gasifiers. You can see the examples. This is one. Again, you see the gas burner, the gasification, and the char chamber with the ash pit door. Okay, but this appears to be a natural draft gasifier. While here you can see the fan, so this becomes a forced draft gasifier. Now, similarly, this is third kind of gasifier which is there. So overall, I believe that now you have fair idea that what are the biomass gasifier stove. It is just like, you can say, modernizing the chula, where you waste lot of energy in the traditional chulas. By using the gasifier stove, you will be able to use more energy from the same amount of biomass with a higher thermal efficiency. Okay. The principle more or less, no matter what kind of gasifier you use, the principle remains same. The only variation that you can see will be in the efficiency or will be in the product composition, etc. Okay, but more or less it is same. So the important part is, how do we reach that this height, like is it should be zero point 0.4 to 1 meter, or the dia should be 0.2 to maybe 0.3 meter or zero point 0.4 meter. How do we reach this conclusion? So to understand that, we will have to discuss about the design of the gasifier stove. So that we will discuss in the next class. This is all for today. Thank you.